There we go. We'll get started.
As he prayed.
All right. So today we're finishing up whatever chapter we're in. 8. I have several votes for 8. Yep. Finishing up chapter 8. What's so giggly about over here? No. No. That'll be interesting.
No, it's not learning process.
That's how easy it is.
You know why my pockets are untucked? Anyone know?
Back to the Future, something like that.
Exactly. Today is the day Marty McFly went back. If you go back, October 21st, 2015.
Yeah.
I also heard today that they projected, or they said in the movie that the Cubs would make it to the World Series.
Yeah.
And the Cubs need to win.
And the Cubs are actually like the best they've been.
Yeah.
But they're still down to the Mets.
That's so great.
They also predicted hoverboards, and John's what, like
17.
19.
Well, the hoverboards do, but it's not.
They're just not. They're not commercially
Yeah,
that
they're
much.
not commercially
And
available.
Anyway,
Nike's
so-
coming out with shoes that are.
They already predicted though, actually.
They already did.
Yeah.
They came out today.
Yeah.
What did they?
So-
The Nike shoes there?
That was why the pocket.
It's amazing what our imagination can do for like
Just put them
our
down.
invention.
I can't.
Yeah.
Because then
I
it's
think that movie has
that's still going to bother Joyce,
caused
isn't it?
people to.
Just to
All
think
right.
how
In
much,
deference to Joyce,
how
I will
much
put my
Star
pockets
Trek
back
has
in.
influenced
As long
like
as Joyce knows you take
inventions
your pockets
until
out
now.
and compensate, that'll be fine.
Like automatic doors
I'll take mine out.
is an invention.
Oh, that looks like it's out to me.
So, Joyce, you just gave me like a whole new like arsenal of things to use against you to bother you. Just like pop out my pockets.
That's right.
You're right.
All right, let's go on. Let's move forward. Only one page of stuff to talk about today. One page.
Let's burn it.
All right. So,
Joyce, is this bothering you?
No. Set
so
fire.
the last thing in chapter 8 is NDE and failure.
It's too underground.
NDE is non-destructive evaluation. Actually, they call it non-destructive testing in here, but 6 of one, half dozen the other.
Never do enemas. Never do enemas.
What's an enema?
That's another good choice.
Never do everything.
All right, so NDE, non-destructive evaluation or non-destructive testing. It's basically a mechanism by which we can. Oh, seriously, guys, focus.
Breathe. It's a Friday.
I don't, it's not a Wednesday. Anyway, it is a mechanism by which we can characterize a material without having to pull it apart and test it. Right, so we talked about pulling it, testing it, stretching it, all these kinds of things. NDE now gives us a mechanism for getting at that kind of information without taking it apart. So, if I want to check the condition of the hull of my ship, I don't have to cut a piece out of the hull of my ship to test the hull of my ship, right?
Is this like the thing you were talking about, like the ball that you press in and you see how much?
So that's actually, that's an example that macroscopically is non-destructive testing, right? So the hardness tester, right? But in reality, it is destructive. It leaves a dent, right? So these are things that are truly non-destructive.
Okay.
So I'm just basically going to go through all the different methods, many of which I've used, some of which I have not. When I get to talk about stress and strain in my general physics class, I tell them that this is the one half of a lecture that I get to actually talk about what I got my PhD in. My PhD is in material science, so it's the half a lecture of my PhD that actually shows up in physics. In this class, this is the research that I did for my PhD, is an NDE. So this is the one class where I actually get to talk about that in terms of the research, in terms of the actual sort of project. I actually did my PhD, the rest of it is just sort of supporting material. Okay, so the first NDE technique we're going to talk about is X-ray. It's used in a couple different ways. We've already talked about X-ray diffraction for a crystallographic system to try to measure the spacing and planes between the atoms. There's not really a destructive way to do that, quite frankly. But the other thing, the way that X-ray is typically used in NDT is radiography. Which is the way that you're probably conventionally used to dealing with X-rays. Like you take an X-ray. What do? You take an X-ray. It's a radiograph, right? You put your leg on a table, and they shine X-rays through it, and there's a piece of film or a digital converter underneath that images the inside of your leg. Right? In particular, images the bone. So an X-ray is typically used for looking at hard tissue injuries, bone fractures and such. In NDE and materials, it's used for the same purpose. So, trying to think of an example. Oh, so an example during the Challenger disaster. You guys know what the Challenger disaster is, right?
You mentioned it.
What's that?
Not that, yeah.
You mentioned it when there was the old guys.
The old guys.
The old dude that was
a near-death experience.
Yeah.
That's the blimp thing.
So in the Challenger disaster, and then in the other one, what was the other? The one that blew up over Texas. What was that?
Was it the 2003 one, or was the Challenger 2003?
Columbia.
Yeah. The more recent one.
Yeah, the more recent 2003. So in 2003, Columbia went up. Actually, for both of them, but especially for the Columbia one, I did some research. I was doing some research at Oregon National Lab, and we used X-ray radiography to look at the leading edge of the wing. Right, there was penetration. There was a concern that there had been penetration of hot gases through that to cause the failure of the. You know what I'm talking about?
Yeah.
Right. So they were using X-ray, actually microfocus X-ray tomography, to look inside these materials, and there's some kind of a strut structure in here. I can't remember what it looked like, but whatever, there's struts in here, and inside one of the struts there was some porosity, little holes. And so they were using X-ray techniques to shine X-rays through it and look at what's going on inside, to look for the holes, but you don't damage the wing in the process of doing it.
Right, so they did this after the thing blew up?
They did it on other struts, they did it on other parts, not on the actual piece that
Did they know that this is why the thing blew up?
they were looking for why it blew up, and so they were looking for issues and problems. I honestly am not sure what the commission ever determined resolved was the fundamental failure, but.
So they have more than one spatial, thought they only have one spatial.
I think
Now they don't have any.
Right.
But they had Columbia, Challenger, Enterprise, and what's that?
Discovery?
Apollo.
Not Apollo. Anyway, there were four, I think.
So they just did this on the other ones?
No, they did this on. They had other parts that were not actually.
Endeavor.
They had.
Actually,
What is it?
Columbia, Challenger, Discovery, Atlantis, and Endeavor.
Oh, Atlantis. I hadn't been away. Okay.
What was it?
So not Enterprise.
We would have never found Atlantis.
Anyway, so the point is you can shine X-rays through it. Now, in materials, especially today, small defects are critical. Right? We've talked about the crack tips. You're looking at cracks and crack lengths, and very small defects can be very critical. So, not only will we use X-ray, we'll use radiography, basically just take an X-ray of the thing. We also use X-ray CT, computed tomography. Right, so you've had a CT, you've heard of people having a CT scan. You have a CAT scan, same thing. Computer aided tomography is what CAT stands for. So you have a CT system where, in that case, you shine an X-ray source on your part, and then you have a screen over here that detects the image. Right, that's how you do a normal X-ray. Well, with the CT, you then rotate either the part inside of that or the X-ray and the imager around it, and look at it from all these different perspectives. So you look at essentially looking at it from 180 degrees, and then computed tomography. You take the intensity distribution and reestablish what's actually going on inside. So you can imagine if I take a simple, oops, who knows how far I'll make it through this class. If I take something that's simple, right, so I have this box, and I don't know what's inside of it, okay, but inside of it is that, right, so I have a box, I can't see inside, but inside there actually is this black, this obstruction, right? If I look at that from this standpoint, I will see bright, 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 dark. Bright, 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 bright. Right, that's the intensity profile I'll get on my screen. If I rotate it to a different angle, so that now, should have done this on the other side. So now my source is up here, and my screen is down here. I'll get something that's bright and then dark for a wider section, right? And actually what I'll get is something that looks like this. I didn't draw that very well. I'll get something that looks, well, if it's a square, I'll get something that looks like this.
Well,
Because I go through a thicker section here than I do at the edges.
oh,
Okay, everybody see that? So, part of tomography, and then as I go around, I get similar things. So what tomography basically does is takes each projection or each image and projects it back. So this image had a dark section here, right? So project it back onto space and say, let's assume that that dark spot was uniformly derived across the entire thickness of the sample. And then the one down here, I project back along this line. Now it's wider, and it's really dark in the center, and it's a little bit lighter at the edges. All right, and really dark down the center. Kind of see what I'm saying? You do that all the way around. And it's not quite as simple as all this, but you do it all the way around, and you can see how, as I continue to do this, right, so I do it from all these different angles, I get light and dark, right? And you kind of can see how I reconstruct the thing in the center. Right? So that's what tomography does. It takes a bunch of different angles, X-rays from a bunch of different angles, and then reconstructs what's actually in there. And there's quite a bit of algorithm to doing this. But you can reconstruct then an actual cross-section of the thing. So in NDE, use this X-ray computed tomography in order to find out what's going on inside the thing without cutting it open. And to use microfocus X-ray computed tomography, where the source is a very small focus point, where this point is maybe 100 microns wide, then you can get very high resolution inside. The smaller this point is, the more accurate all your tracings are. Okay. So microfocus X-ray gives us very high resolution, and that's what found those little tiny porosities in the middle. So, X-ray. Next, ultrasonic testing, UT. So here we're essentially, there's two flavors that we'll talk about: conventional and what's called phase array. And this is basically sonar on a micro scale. Everybody knows what sonar is? Right? You send a ping, and you listen for the echo. Right? So that would be pulse echo sonar or pulse echo ultrasound. So if I have the same specimen now, here's my specimen, and it's got this thing inside, and I don't know where that thing is, or I don't know anything about it. What I'll do is I'll come along with a transducer here at the top, and I'll send out sound waves and listen for the echoes. And when I'm at this point, what I hear, my signal intensity, as a function of time, will look like this. Where that is the echo off the back surface of the sample. Right? But then when I'm over here in this position, and the sound comes out, what I'll hear is I'll see this, and I'll go, right? And then I'll get a little thing there, because a little bit of the sound goes through that thing. And maybe, depending on what that is, if that's something that has a higher speed than the part around it, or the speed of sound in the black is higher than the speed of sound in the white, see what I'm saying? Then I'll actually get this little thing here. And then I'll get another, another one. Because this is the second reflection where the white is, the sound has gone down and back and down and back again. You follow me? It's the echo, echo, echo. Right, you get multiple echoes. Right, so this is echo, 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 echo. Actually, technically it's echo, 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 echo. You know what I'm saying?
Wait, how does it go again?
You know.
No,
Okay.
no.
And so what I can do is I can plot the time of arrival of each of these pulses. And in so doing, this one has an early time of arrival, so if I plot the arrival time on this axis as a function of position, the late arrival time is down here, then all of a sudden there's an early arrival time, and there's a late arrival time as I scan across the sample. Right? See what I'm saying? So that tells me where this thing is. As long as, and I can turn it into physical position if I know the speed of sound in the material. So if I know the external dimensions here, I can look and say, okay, well this time t here, t b for the back, right? This is 0 over here. I know that, and if I know the dimensions here, x, then I know that 2x divided by t to the back is equal to the velocity of sound in that material.
Assuming you know that there's no obstruction at that point.
Right, if I know that that's indeed the signal.
So if ultraviolet is high energy short wavelength light, ultrasonic, is that just related to the wavelength of the
High,
sound?
yeah, it's short wavelength sounds.
So it
Or
could
high
be-
frequency.
It doesn't have to be high amplitude, just high
Right,
frequency.
right, it's not high amplitude. I mean, you don't hear it, so you don't really know. It's beyond your hearing. Ultra means beyond human hearing.
And the frequency, not.
Right, right. Ultra, it's a higher frequency than what you can hear. So anything above 20 kilohertz is basically considered ultrasound. But the key here is, in most of these things, you want to be able to get spatial resolutions. You want very short wavelengths in order to be able to resolve very precisely where the little defects are. Short wavelengths means high frequency, so you typically do this at 10 megahertz. That would be a common frequency for doing conventional ultrasound testing. Okay. Does that kind of make sense to everybody, that process? Okay. And actually what I'd really see here is I'd see another spike from the back surface here that might be lower. Right? I'd see it from, so I'd get a reflection from that surface, a reflection from that surface, and a reflection from that surface. Okay. So I would know, oh, there's another thing back here too. And I could actually get the whole size. Okay.
So all you really know where this is where the surfaces are. How do you know that it's not? How do you know that that's
There's additional interpretation that's involved. So in other words, I don't know where this back surface is because I don't know what the velocity is in this one. So I have to look for, okay, here's the back surface, here's the front surface of that thing, here's the back surface of that thing. Then there should be another front surface reflection and another back surface reflection because the sound will keep going back and forth between those two as well. So I can use this, and or I can use this and this to find the speed of sound in that material, and thereby place the back wall. So you get a whole bunch of reflections, you get a whole bunch of spikes, and you've got to be able to interpret those spikes based on what you do know to find what you don't know. That make sense? So I think there's at least one problem in your homework that talks about doing that with ultrasonic testing. That's conventional ultrasound. And typically speaking, these transducers here are focused, or at the very least longitudinal, so that the sound is actually coming out not sort of randomly, but they're coming out as plane waves. That the sound is directed straight, and so you don't hear echoes from the things off to the side. Or oftentimes they're actually focused, down to some particular depth. So there'd be some focal point. So the sound is concentrated within this center spot to keep the sound, the spatial resolution good, to get the lateral resolution good. Make sense? Okay. So that's conventional. Phased array ultrasound is very similar, but with phased array ultrasound, this is nothing in your book doesn't talk about this at all, so you just have to weigh in here. Phased array ultrasound. There's also phased array radar. For anybody that's sort of more electrically interested, do the same thing in radar. Actually, it was done in radar before it was done in sound. Instead of having a single transducer up here, I actually have a whole bunch of transducers lined up side by side. And the transducers are usually some kind of piezoelectric material. Does everybody know what piezoelectric means?
No.
Mechanical to electrical.
What's that?
The mechanical kind of like interface between mechanical and electrical with
Right.
the crystal and stuff.
So a piezoelectric crystal is a crystal that changes its potential in relation to the force that's applied to it. So I take a crystal, if I squeeze it, then it has a high voltage. If I pull it, if I could pull it apart, then it would be a negative voltage. So there's a voltage created on the two faces of the crystal based on the force that's applied to them. So usually you guys are used to piezoelectrics and speakers. And so I'm guessing that the speaker that's in here is a piezoelectric crystal. So they apply a voltage to this thing, and as a result, it expands and contracts in response to the voltage. Just like an expansion or compression applied creates a voltage, and applied voltage creates an expansion or contraction. So I can get this thing to expand and contract and create sound. Okay, is everybody good with what piezoelectrics are?
If you squeeze it, do you get shocked?
No, it's not high, not that high voltage. No. I mean, you could, if you had a big enough stack.
If you have like a lighter, like sometimes lighters have little piezoelectrics. If you take it apart, I did this one time. You take it apart,
Yeah.
it has a little wire, and the light shocks you. It's really cool.
Why do lighter? Oh, not the lighter.
Right, so you know what I'm talking about?
The clicky
You know
kind,
what I'm talking
not
about?
like
Yeah, the clicky kind of lighters, right? It gets a little spark at the end, you know, the grill lighter. Right? It goes click, 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 right? And every time there's a click, there's a little spark at the end. So what's happening there is there's a spring-loaded mechanism that pulls in, and when it clicks, the spring lets go and smacks that thing. Hits it with a very high force for a very short period of time, create a very high voltage, which creates the spark across the gap.
That's cool.
So that's why it clicks. You know, it's not just a gradual push, it's a click. Anyway, okay. So, transducers are typically made of piezoelectric material. Okay? So we have here the piezoelectric material, but now instead of having one chunk of piezoelectric material to which we're applying voltages, we now have a whole bunch of them. And we can control each one individually. And so now what will happen is I'll fire the outside ones first. And then later the inside ones, and then this, and so on. So I control when they fire. Boom, 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 boom. Okay? The first ones to fire then, the sound has propagated some distance before the center one fires. And then this one propagates an additional distance, the center one here, and then this one out here, right? You can't see what I'm saying? So what you end up creating is a wavefront between those. So that there is some point down here in which all of the wavefronts arrive at the same time. And it takes longer for the ones at the outside edge to get to that point than it does the ones in the center. So I can focus my energy by getting all of the waves to coincide at that point at the same moment in time. And it turns out the energy goes as the square of the amplitude. Right, you guys are familiar with that? Right, okay. So if I have amplitude from all of these hitting at the same point at the same time, then the amplitude adds, there's superposition of amplitude, but then there's a squaring of that amplitude for the energy. So I deliver the bulk of the energy to that single point, right?
So,
And the advantage of this is I can then steer that by just changing the timing at which these things go off. So if I delay this one further, or if I delay this one longer and fire this one earlier, I can steer this to point over there instead of pointing over here.
What does that achieve focusing the energy?
So that, in other words, if you're looking for a small defect, you know, that's just this big, a little micro crack, right? If the energy's focused, then as this thing passes over that micro crack, I'll get a big signal because now I've got all the energy at that point.
Bigger than if you had just one transducer.
Bigger than if I had one transducer, because one transducer's energy would not necessarily be focused. If I had one focused transducer, I would have the same result, similar result. The advantage to this is I don't have to keep moving my transducer mechanically back and forth across the surface. I can take this thing and just digitally, right? I can scan back and forth just by changing the timing between when I fire the transducer.
Here's a question. If you're firing these things, if you're updating the firing, rate of these things continuously, wouldn't you get reflections from a
Right, you have to
position?
space, yeah, you have to space them out. You have to let the sound dissipate before you can go on to the next firing. But it turns out, the sound moves pretty quickly through these materials. I mean, the speed of sound in steel's between, let's see, in steel, it's, I think, 5,000, I can't remember, it's 5,000 or 7,000 meters per second. Okay, it's fast. So if I've got a steel, piece of steel that I'm checking out, the sound very quickly dissipates in that, so I can move on to the next scan. And I don't have to physically raster back and forth across the surface. So that's the advantage of phased array. It does the same concept, it applies the same concept, it's just a faster way of doing the inspection. Yeah.
So would you normally have like your whole surface covered, or would you kind of?
Well, yeah, you can't.
You move your
Right. You
thing
typically scan in one dimension, but then so you'll scan back and forth here, but then you'll scan this thing along this direction. And then if it's a really wide panel, you'll do another strip. But you do it in strips. You'll have to do 1, 2, 3, as opposed to going 1, 2. I'm saying instead of make this thing mechanically go back and forth, it takes forever. Ultrasonic testing. Good. Basically sonar on a smaller scale. Next, infrared. Everybody has seen this on television, right? So you've seen Predator. Who's seen Predator? Or AVP, one or the other.
Not me, I'm
No?
sorry.
Scary for you? Okay. Predator, you know what I'm talking about, Predator, right? Two people who know what I'm talking about.
I know what you're talking about.
The bad guy from space who sees in the infrared.
The violin player from Dave Matthews Band. Have you never seen that?
No.
Okay.
Okay. Anyway,
Sounds like a sick reference, that.
anybody seen the new Minority Report?
No.
New TV show? All right.
We don't have time for TV shows, come on.
What did you do?
Okay. Has anybody, you've seen thermography, you've seen people looking for infrared heat signatures, right?
Every single military movie.
Stop. Right. So infrared is just looking for heat, right? It's imaging heat. Because heat, Q, we talked about in thermodynamics. Apologies to those who are not in thermodynamics. Q is emanated. One of the ways that Q comes off, the heat comes off, is radiation. And the radiation is, the temperature difference determines what the wavelength of the radiation is, but most heat is given off in the form of infrared radiation. So infrared NDE, infrared NDE, is basically just looking for thermal signatures. So if I have, there's a couple different ways I can do that. If I have something that's got a little crack in it, right, and I'm flexing this thing, that crack's going to rub against itself, and it's going to create heat, frictional heat. And so if I have this cracked specimen and I'm tensing it back and forth, there may be a hot spot where the crack is. So I can use infrared thermography to find the hot spot. The more common application for infrared thermography is if I have some kind of a sample and it's a layered structure, like a composite material, which we'll talk about later. But you know what I'm talking about by layer. So I lay down, you've seen,
Like plywood.
yeah, like plywood. Okay, it's like plywood. Okay, it's high-tech plywood. Okay? So I lay these things down on top of each other to give it good strength. You guys understand the concept of plywood, right? A different fiber running in a different direction. So but that plywood loses its ability to be effective if in the center here, there's a gap. Because now the thing's not glued together, it can rub back and forth, and there's, you know, if I stretch it, it's not able to withstand the stretch. It's not able to withstand the stress. So I want to find those things. So what I can do is I can get it hot with like a flash lamp or something that's really bright and intense. Gives a bright and intense flash. Right? So I put in a whole bunch of thermal energy over a very short period of time. You can just think of like a flash bulb. Well, you guys don't even know what flash bulbs are.
I do.
Yeah, we do.
The ones that
flash, do they like,
The ones that
is it a
like
bulb that like
burn themselves
That we
flashes?
do for,
The ones that like burn themselves out.
Yeah, the ones that burn themselves out, that's what I'm talking about. So, you know, back in the day, cameras actually had disposable flashes that you put on the top and really bright light, very short period of time. So you have these, and these are not disposable, these are, you know, just bright halogen sources. And essentially you charge up a capacitor bank, a huge capacitor bank to an enormous voltage, and dump all that charge, all for 1 second, you get this really bright light. Okay, that light gets absorbed by the backside of the surface, gets hot. But where this gap is, the thermal conductivity is compromised. Right? So I can't get the heat to come through there. So then I look up here at the top with my infrared vision, or an infrared camera, for those of you who don't have infrared vision. And what I see looking down on it is I see, okay, here's my plate gets hot, except there's this one little cold spot in the center. Actually, it's cold, so I should draw it in blue. There's this one little cold spot in the center.
Well, if you're shining light, why don't you just look for where some of the light comes
Because
through?
it's opaque. It's opaque.
Yeah, but just use X-rays
Is it
instead.
like a hole?
Because X-rays are a heck of a lot more expensive and a lot more dangerous. I have an infrared camera in the other room.
Yeah.
Right? If I wanted to do this, I could do it here. I could do this in the lab.
We test ourselves.
In fact, one of the projects I'm thinking of doing for undergraduate research, maybe next summer or the summer after, would use the infrared camera for doing something like this. Except the excitation in that case, instead of being a flash lamp, a light, is going to be microwaves. So I excite with microwaves, get something hot with microwaves, and then see where the hot spots and cold spots are.
But I would assume that since this is not a structured evaluation, it's not hot to an extent that it's dead.
Right. It doesn't burn the material. Right?
Do you also
It's hot
want to
in the
have-
sense that thermography can see just fractions of a degree difference.
Doesn't this only work for relatively thin samples?
So the thicker the sample, the more diffuse this gets, right? So if it's a relatively thin sample, I get that kind of signal. If the sample's too thick, I get some kind of a more diffuse thing, and I don't really know as much about it.
What if you knew the ideal material properties of the substance and the thickness of it? Could you, that would be kind of interesting.
Right, exactly. Okay. But does that make sense to everybody? You can kind of see. And again, with infrared, we're characterizing the thermal properties. Over here, we're characterizing the mechanical properties. And with the infrared, or with the X-ray, we're kind of characterizing the geometrical properties. Right? Although to some extent you get the chemical properties too, because different substances absorb X-rays in slightly different ways. But nonetheless, it's the kind of properties you're looking at that vary. Wow, I'm really not going to make it very far through here. Stress corrosion cracking anywhere. Oh. Okay, I'm going to have to pick up the pace. Another one is eddy currents. Everybody know what eddy currents are?
Isn't it like the magnetic field thing?
So yeah, if I have a coil, into which I put a sinusoidal oscillation, right, that coil is going to create magnetic field going in and out of the board. And that magnetic field will oscillate sinusoidally as well. If I take that coil now, and I'm going to view it from the side, and put it near a piece of metal, that changing magnetic field will penetrate the metal and create currents that move in little eddies in circles. So I put that coil down on the metal, or against near the metal, and I'll create the same matching currents in the metal itself, in the skin of the metal. So I create currents in the metal in opposition to the currents that I'm applying because of the desire for the metal to keep the magnetic field constant. Does everybody understand that?
Just in the surface.
Penetration depth, well, I mean the B field, right? The B field actually does this, right? It's like a big butterfly. Right, so it's most intense right here. The eddy currents that are out here are going to be much smaller. The currents spread out. Okay. So the idea with an eddy current is to probe the conductivity, the electrical properties of the surface you're inspecting, right below the thing. So if I scan my eddy current probe across there and I find a place where there's a crack in the metal, then I'm not going to get current flowing across that crack. And so I'll see a response in the eddy current probe. The eddy current probe actually not only excites, you usually use the same probe to excite and measure the response. So you excite it and then you listen kind of electrically, you don't really acoustically listen. You listen for how the material responds. Anyway, so as you scan across, you're going to get a change in electrical properties here, which is going to manifest as a signal in the eddy current probe. Yes?
Now, is that kind of how like a metal detector works?
Yes, that's exactly how a metal detector works, except this is typically done on a much smaller scale. Okay. Good? Make sense?
What's doing the actual detecting?
So you can have two different coils here, and you'll get a different response. You know, the second coil, there'll be a phase shift or an amplitude change in the second coil due to the presence of the defect. Or you can actually use the same coil and just make it, you know, it's a more complex problem, but you can use the same coil and look at the, what it takes to drive it, because as the response from here changes, it will take a different amount of current and different phase of current to drive this in order to keep the same thing going.
So where would you sense that? Would you sense that on the metal itself?
You sense it in the coil. You sense it in the coil. You sense the coil, yeah, you sense the response of the coil up here based on the eddy currents that are generated in the metal, which are the result of the coil itself.
So you'd have to sense off of that with some sort of contact? Like
No. That's what I'm saying. You have another coil, and as I just said, you can have a second coil up here, maybe, that senses the response of this one. You can sense the B field from this, and the B field from this, right? Sensing both of those at the same time. But when I get over the crack, the B field from this will change. And so the response of my other coil will change. And again, you can combine those two coils into one coil if you're creative about how you do it. Okay. I'm just going to skip terahertz. That's actually another thing I'd like to do. I'd like to be able to get a terahertz spectrometer. So terahertz is just, infrared is here, visible is here. After infrared out here is radio waves, microwaves, as we get longer and longer wavelength going that direction. The space in between infrared and microwaves is called, it's the terahertz range. Right? So it's terahertz frequencies. Right? So these are much lower frequencies, these are much higher frequencies, these are terahertz. Light, for instance, is hundreds of terahertz. Hundreds? What's the light? Times 10 to the 14th, times 12. Yeah, hundreds of terahertz. The 400 terahertz to 700 terahertz or something like that. I can't remember the exact numbers. Anyway, infrared then is going to be tens of terahertz in this terahertz regime in here, and then the gigahertz regime down here, and then radio frequencies down there. So you can do radar, right? We do radar all the time, looking for big things in the sky with big wavelengths, radio waves. If you do radar, but use terahertz waves, which have wavelengths that are on the order of millimeters, then you can do the same thing, but you can look for much smaller features in a much closer environment. Does that kind of make sense? So you can use terahertz waves in solid materials to probe down in and look for small features, the same way that radar looks for big features. So it essentially becomes ultrasound, but instead of using mechanical waves, we're now using electromagnetic waves. But the electromagnetic waves will interact with the things underneath, you'll get echoes the same way you do in radar. It's all the same concept, just applied on a smaller scale. The downside is, to using terahertz is that they're extremely strongly absorbed by water. So you can't do it in an aqueous environment, and even humidity can be a problem. So you have to do it kind of in a dry environment, or at least on short distances where the humidity in the air doesn't absorb the terahertz. Okay. So another terahertz. Okay, that's as much of the NDE. Last 10 minutes I'm going to go through a whole bunch of different failure modes that I think most of these are probably mentioned in your book, but I want to make sure we've covered them all. Some of them we've talked about already. Some of them are new. I want to make sure you've at least had an exposure to them. For anybody that's interested in keeping track of terms that I might want to know the definition of which I might know the definition. Okay. So we've talked about ductile fracture. Right, that's when you go all the way through the stress strain curve, and you break out here, that's ductile fracture. You ductily deform the material, and it breaks. Right. Ductile fracture typically looks something like this. If I have the two samples, if I pull on a tensile specimen, it might break, something like that. But this is like a round bar that I'm taking a cross section of. This region out here is ductile fracture.
But what have you done? Is that like the crack after you
This is the cracked pieces after they've broken apart. Okay, so I'm pulling on the bar and it cracks apart. This out here, these side regions are ductile fracture. Right? That's where remember the resolved shear stress, right? If I randomly orient all my grains, it turns out that the Schmidt factor that matters is 45-45. Right? This is where I'm going to get my maximum stress. If I go to 45 degrees to the plane, 45 degrees, you see what I'm saying? The cosine of 45 times cosine of 45 gives me my maximum stress. It's square root of 2/2 times square root of 2/2, which becomes 1/2. That's the maximum Schmidt factor I could ever get. Right? Because if I start tilting beyond 45, I'm pulling stronger, but my area goes lower. Everybody see that? So what happens is you get what's called shear lips on the sides, because that's where the thing shears. Shear is a form of ductile deformation. And so I get the thing sliding past each other, breaking at that angle. Down here in the bottom is where I get the brittle fracture then. Because what happens is, I crack it out here, and then eventually down here at the bottom, I no longer can support it. And I can't even support additional deformation, then it just fails brittle. Does that kind of make sense? Okay, so you might get that kind of, you don't always get this, I'm just saying this is an example of how you might get the difference between ductile fracture and brittle fracture. And we also talked about the brittle to ductile transition temperature, the DBTT, for the Liberty ships.
Yeah.
Right, so differentiate between brittle and ductile fracture. We've talked about fatigue. We've talked about fatigue, both dynamic and static fatigue. The idea there being that you have some local imperfections causing plastic deformation, even though the macroscopic stress is well below that necessary to cause failure, well below the ultimate consensus. I talked about corrosion fatigue. Corrosion fatigue, which we call, or also called, stress corrosion cracking.
Simple cubic.
So we have dynamic fatigue, corrosion fatigue, kind of like static fatigue. And then I said it was analogous to stress corrosion cracking. Okay. One failure mechanism we haven't talked about is wear.
Where?
Wear.
Are we talking about this?
So, you know, your tires, right? You ever have a blowout with your tires? Right? Problem with your tires is you keep using them, they wear down, they get thinner, they eventually can't handle the stress. So wear is a problem. If you've ever seen like a bearing that's gone bad, the shaft going through the bearing will have a bunch of grooves ground into it because the bearing has gone bad and so the shaft has worn a groove. Okay, so wear is the study of wear is tribology. Tribology is the study of wear.
Study of
Okay. You guys, I feel like we're just being a little cute today. You follow me? The why wear is a problem. That and wear is what we would typically refer to if it's a solid on solid contact. Erosion is what we call if there's a liquid on solid contact. Same idea. But water rolls over it long enough, for a long enough period of time, it can erode. Another form of failure.
Like water jet works, right?
Right, exactly. So I talked about hydrogen embrittlement, where hydrogen diffuses into the interstitial space in a metal and weakens it. As a result, makes it more brittle, prevents the dislocations from propagating, so it makes it fail in a brittle mechanism when it should be ductile. There's also liquid metal embrittlement.
Is that H embrittlement?
Hydrogen embrittlement, yeah. Liquid metal embrittlement. Something that, actually both of these are things that Blake will come back and tell us about sometime. Both are major players in nuclear industry because they use liquid metal to cool. There are liquid metal cooled reactors, not all of them are liquid metal cooled, but there are liquid metal cooled reactors, and obviously you have free alpha particles flying around, that's hydrogen nuclei. So both of those are and what happens is, again, it makes the stress, you get stress concentrations from the intrusion of these species into the matrix, and the microcracks are propagated by the virtue of those stresses that are created. And then we talked about creep. So those are the kind of failure mechanisms we've discussed. I think that covers everything. I don't think there's anything else that I'm going to hold you responsible for that isn't somehow connected to that list. Any questions? Okay, so I think the only place that I get quantitative in the homework is with the ultrasonic testing. So you need to make sure you have an understanding of that. What's that?
It's all quantitative.
It's all quantitative?
On the homework?
Yes, but I think the only one of these that I use in those problems is ultrasonic testing, because X-rays, are they both ultrasonic testing? Okay, but that's what I'm saying. That's the only one where I'm asking you to be quantitative. The rest of these are largely qualitative descriptions. Short answer is